for this second lecture, which is once again which we have already informed. It's going to be introductory, so that we make ourselves compatible with the mathematical concepts which we are going to need when we go to the quantum mechanics. And today what we will do is we will once again first of all go back to the concept of the vector spaces, and we will review whatever we have said earlier in the last lecture, but we will kind of deep dive again into the concept of the linear spaces, or what I call as what we also call as vector spaces. We will to make sure that we understand, we are very compatible. One is that we understand these things, and secondly, we are making ourselves very compatible about these concepts, because as we know, I mean, we will also explore it later on. As we know, the state space of quantum mechanics is a vector space, so it becomes very important to make ourselves compatible with the concept. What do we mean when we say a state space of quantum mechanical system is a vector space? So we have to understand that that concept very well, and surely its physical and mathematical consequences. So let's go ahead. I'm sharing my screen with you all, so then we will go ahead with these things. Okay, I hope you are able to see my screen, the whiteboard which we have. Okay, so let's go straight to the discussion where we last left, and it was about linear spaces. Okay, so, and right in the beginning, I want to highlight that there is a difference between linear space and vector space, and we will surely come to know about the details of the differences. But for our today's discussion, today's lecture, there should be no ambiguity in linear space and vector space. So vector space is actually which we are going to, I would say mathematically it has a richer structure as compared to the linear space. But we are in the beginning, we are going to explore linear spaces and try to see the structure which these linear spaces have, and what does it from the physics point of view, what does this linear space and the structure on the linear spaces mean for us. And as we have from the last lecture itself, we have begun to give you a totally unconventional, a very novel point of view about these things, which is not a kind of a usual standard textbook approach to understand linear spaces. Rather, it emphasizes on taking a physics or a physical based approach to understand what a linear space is, because it is not for us sufficient to just know the definition of a linear space. For us, it is also important to understand why would linear spaces emerge, or why would they get involved in, why do we need to use them in physics, especially in quantum mechanics. The relation between linear spaces and quantum mechanical and the physical systems should be made very clear. There's a clear-cut correspondence between linear spaces and vector spaces, and the related concepts and the structures, and between the physical systems and the physics which we do. that correspondence needs to be made very clear if at all we want to explore quantum mechanics, because one of the main challenges which students or the beginners typically face, or this is generally, in fact, this is generally true for whole of the theoretical physics, that there's a broken link between mathematical structure which we are using, or the mathematical formalism which we are using, and the physical physics part of it, or more, let me call it physical reality of it. There's a missing link and the broken link between them, and it's because of that broken link we struggle, and the beginners struggle, and some of them never get to master the subject. So our approach in this course is to bridge this gap and to make these things very clear, so that each one of us can easily bridge between mathematical structures or the formalism of quantum theory to the actual physicality of it, to the actual physics of it. Okay, so therefore what we do is that we start right from the beginning, and the linear space is the basic structure where from we start. Okay, and what is and then we go to the vector spaces. We will see vector spaces have though vector spaces have a richer structure. One thing which I want to mention right in the beginning is there are inner products defined on a vector space, while as in case of we will see, I mean, we will explore those things also, but to emphasize that vector space is also a linear space, and we would first of all explore their linear part of it, linear structure of vector spaces. Okay, and that's why we have mentioned them, though I could have mentioned them as vector spaces, but to emphasize this fact that there is by definition a vector space does not have any inner product defined on it. It's only that we have to bring in this extra structure later on because we need it. So therefore that's why I named them linear spaces rather than calling them vector spaces. And it is a very simple structure as we have explored last time also, but we have to appreciate and see what is the power of this mathematical structure which a linear space has. And let us summarize, let us see what we did last time. So first of all, we gave a very different kind of a definition of a linear vector space, which was that we defined a linear space as a space, okay, in which what we have a linear superposition as one of the defining properties of that space. So all the elements, so you can always the elements belonging to the linear space, which we call as vectors, okay, vectors have this property that you can always linearly superimpose them to get the new vectors. Okay, and so linear superposition is the defining property of a linear space. So we will see it leads us to the definition, or to the whole determine, we can fully determine our linear space if we have the linear superposition with us. We can begin with the linear superposition. And I just gave you some important examples which typically we don't talk about. When we talk about vectors, we do not talk about ordinary differential equations. We typically talk about our well-known geometrical example, which is the R3, and we will surely come back to that well-known vector space, which we know from the very beginning of our careers. So, but I want to it is not the Euclidean space which has too much of relation with quantum mechanics. The vector space, the Euclidean vector space, and the vector space which we use in quantum mechanics, they are definitely both vector spaces. However, the structure, the essential nature of vector spaces which we use in quantum mechanics are more closer to the solution space which we have discussed last time. Therefore, the choice of this example was deliberate to elucidate and demonstrate to you that later on you will have a recurring discussions about the solution space. And in fact, if we just say just for the sake of making a connection to quantum mechanics, so the vector spaces which we use in quantum mechanics are basically solution spaces of a differential equation. As you would have noticed that you have a differential equation over there also, which we call as a wave equation, and then you have the solutions. You have vectors, the state space vectors are basically solutions to that differential equation. Same thing we are doing here also. We are taking one of the very well-known example we have taken last time this example of one of the very well-known system in physics, which is one of the favorites of all the theoretical physicists, which is a case of the simple harmonic oscillator. And this is the equation of motion for a simple harmonic oscillator. And this is not just any equation of motion, as you would have studied equation of motion in kinematics and other areas also. But this is a very, very special equation of motion. And let me just give you a guess, just give you a hint about why is it special, and we will be coming back to this equation again and again. So in German, special is called eigen. Okay, this is just a hint for you that why is this equation going to be important for us, and we will later on come to it. But just to give a hint to you that in German, and the people who are developing quantum mechanics, some of important people were from Germany. So in German language, the special word we use, the corresponding word in German is the eigen. And I think you remember now what are the eigen, this word we as a prefix. Why do we use this word in quantum physics? And this equation of motion is very, very special with respect to that. So and what we discussed last time is that the solutions, this equation of motion has definitely two linearly independent solutions, which we write as, first of all, let me write the solutions themselves. Let me call them y1 and y2. So, but this is a property of the linear superposition, which tells me that you can always write down a linear combination of these solutions, and you will still have another solution. And we will, so which is called, this property is called closure property in mathematics. What it means is that you have a set of vectors, or you have a set of elements in a given set or a space, and then you do there's an operation which is defined on them, and you can always do that operation, binary operation, whatever you get as a result of what we call as resultant in vectors. So that resultant is once again a vector. It belongs to the same space. This is called a closure property. And that's what linear superposition also tells us, that if you start with two vectors or more vectors, two or more vectors, you take a linear superposition of them, what you are going to get is once again a vector belonging to the same very space from which you have taken the first two vectors. Okay, this property, so superposition tells us that there is already a closure property satisfied by these vectors, and this is what you also need in a vector space. Okay, I am just highlighting that how always you have studied linear superpositions. I'm just trying to bring to your attention that whenever you are studying linear superpositions, you are already always using the mathematical structure, the underlying structure of a linear space, always. And that's how linear superposition work. Now we are turning tables around. What we are going to do, we are using these linear superposition principle as an example for us to learn about linear spaces. Okay, so this is what is happening here. And as you can see, just in this equation, a very, very simple equation, I think one of the simplest equation which we can write down here, and it has a striking resemblance to the things which we have learned early on. I mean, I just cannot resist myself in writing that down. Rather, we were writing it in this language when we were very young. So we used to do vector algebra, and it used to be in this language. Let me write it E1 plus, or rather E1 is fine. So then E, okay, E2, okay, then, or if you don't like it this way, let me call it EY and EX plus Z and EZ. Okay, and we used to call this particular property of vectors as vector resolution, and it was one of the very important properties of vectors had. In addition to that, you can add them. It's basically other way around. What this equation does. So what I have written over there in this equation is exactly same, not similar. It's exactly same as we study in vector resolution. So vector resolution is also an example of linear superposition of vectors. So you would not have noticed it, because when you think of linear superposition, typically you think of waves and oscillations. You think they have this property of superposition, but even vectors have this property of superposition. Superposition is a general property of vectors. In fact, this is as we are taking this as the way we are understanding linear spaces. We claim that superposition is the defining property of the elements of a vector space. Okay, or a linear space, what we call as. So what is happening here, just let us spend a couple of minutes in seeing what's happening here mathematically. What are the operations which are happening here? We see two things are surely happening. One is there's an operation which is that of an addition. So we have a vector addition defined on this set of elements, set of vectors, set of solutions. Okay, and then so this has to be defined, and then only, so unless you don't have this vector addition over there, you cannot take a superposition. Okay, that's one thing. Second important thing which we do not emphasize too much on it is that vector space or a linear space cannot be defined. It is not something which has to do just with the vectors alone, as the name may suggest. From the name you may think that it has something to do with just vectors, but that's not true. Vector space is combination of two types of elements, two types of members. One, we call them vectors, and another, which we call numbers in maths, or we can call them scalars also. Okay, so these members are the scalars over here. Okay, numbers they can be, like as in quantum mechanics, we do not use these scalars are complex numbers. Okay, and it's very, very important to have complex numbers over there. But in general, when we have many vector spaces where we use real numbers. But this is to be emphasized that for a vector space, the full membership belongs to two classes. One is the vectors themselves, and then you also, without scalars, you cannot define a vector space. Okay, that's what's happening here. So you have these scalars multiplying the vectors. So you see this element here, C, and then times y1. So I'm not putting any kind of an arrow over there. So we should not understand this is not a vector, because this is a different kind of a vector. And maybe you have not thought too seriously about such kind of vectors, but it is these kind of vectors which we are going to deal in. Okay. And what kind of, so first I want to see there's a multiplication happening over here. And this multiplication is a scalar multiplication. Okay. And a vector space or a linear space has both the things. It has vector addition. So where a vector, you can add vectors, you get a vector. Okay. And then there are some interesting properties of vector addition. Then it has also a very important operation without which we cannot have a vector space, which is you have this ability, which looks very trivial thing, which looks like it should come as a kind of a byproduct. It should be always there. I mean, if you buy, if this was a product, if you went to a market and buy vector spaces, you will assume that the scalars will come as a byproduct of them, as a kind of an offer, top-on offer on them. But no, they have a fundamental role over here. So in some sense, vectors and scalars are more or less on the same footing here, because you just drop the scalars from the list, you do not get a vector space. This is very, very important. And so therefore, so we have these two guys. So you have a scalar multiplication here. That's another operation which is defined on a vector space. So we have two different operations defined on a vector space, and that is what is needed for a linear superposition. If you have waves and they have to superimpose with each other mathematically, because they are solutions of a differential equation, of a wave equation, mathematically they have to be members of a vector space. Then only they will have these superposition principle being true, or they will hold that thing, that thing will happen, interference will happen. And for that, they will need both the things, the vectors as well as the scalars. Okay, this is something to be highlighted. And what are your scalars? These are your friends, old friends. You used to call them vector components. Okay, so where are these scalars over here? Let's go back. So I am once again deliberately bringing this vector algebra. Otherwise, there is not too much of need of it. But I just to have a continuity of your physical intuition. You would have learned certain things already. You are compatible with them, and then you are going to a different domain, which is a quantum domain. My interest would be, or anybody's interest would be, from a pedagogy point of view, what is it that what already I know, can I carry some part of it to the quantum domain as well? My answer to that question is that yes, you can carry on all those things. In fact, what you studied in vector algebra, it is just that you have to make a proper correspondence. So I will, in a moment, I will tell you how is the vector spaces which we use in quantum mechanics. I am going to tell you some of the differences as well. But here I want to highlight one of the important similarity, which is, as I said, I was telling you that we use these scalars they're very, very important, these scalars in a vector space. And I just want to give you some, we just want to go slowly over it so that you have enough time to think about it, grasp it, appreciate it. That why is it that when we talk about vectors, why do we in the first place need, what we have to do with the scalars there in a vector space? And let me give you an example. So these scalars which I'm talking about here, they are important. We use it to call them as components of a vector components. Okay, in x direction, in y direction. So these scalars make the components of a vector in a particular direction. Like I have an x component, y component, z component. So all those components, they are not themselves vectors, they are basically numbers. In fact, if we write down in a component form, if we write down our vector v from the vector algebra, we use it to write it as, let's say, vx, vy, and vz. So in this way of looking at vectors, vector is basically what we call as an tuple. Okay, it's a basically ordered list of numbers which has some interesting property, which is like that this tuple has to satisfy vector addition. It also has to and the related properties, and it also has to satisfy scalar multiplication and the related properties. And these things we already, I mean, when we were dealing with, when we do vector algebra, we are using these properties without noticing that these vectors have this property. We assume there is some sort of a hidden assumption about these vectors, and that's why we use it to do that. in this lecture, we want to highlight those hidden assumptions and bring it forth. That's what we do in a mathematics. We bring it forth. We look at a structure which we have already used. We would have used it in physics. We would have used it somewhere else. But in mathematics, we want to look at that structure and appreciate it, highlight that particular space has that structure. Okay. Before I forget, I just wanted to mention here that there's an important difference between I mean, somebody may ask me a question. If you are saying that in the vector algebra we have a vector space and we have all the properties of the vector space which we use in vector algebra, and then how is it that is that then I am using vector algebra in quantum mechanics? So in some sense it is true. Definitely we are using the same vector spaces. However, there's a slight difference. The difference comes from the following fact. The vectors which we used in vector algebra, so they belong to a real space. We have a Euclidean space, which is a space which we experience in our daily routine life. So we have a Euclidean space, which is a space out there. Fine. Let me call it. It's actually true to call it real space. So it's a real space. Okay. And then there are elements in the vector algebra. What we use it to study is this Euclidean vector space as a vector space. Okay. So this is what we use it to study and use its various properties, especially the superposition property that allowed us to decompose a vector into its various components. Okay. But in quantum mechanics, there is going to be a difference. The difference is that we are not going to concern ourselves too much about this vector space. Okay. What we are going to look at is something called a state space, and that state space is once again a vector space, but it is of a kind what we call as solution space, which we talked about last lecture. In our first lecture, I deliberately highlighted to you that let us look at we could have easily started with the Euclidean vector spaces and then talked about vector spaces, but that's not the route I wanted to take for a deliberate reason, because those vector spaces are not exactly the ones which we use in quantum mechanics. In quantum mechanics, we use vector spaces calling solution spaces, and these are mathematically we call them as function spaces. So here is a very interesting point of view to be noted, and I will go very slowly over it, very slowly over it. So in quantum mechanics, we do not have, I mean, the real Euclidean vector spaces, they are there because they give us position and position coordinates. So that's there in the background. Those things are there, but we concern ourselves. The place where vector spaces come in is in the point where we talk about state vectors of a quantum mechanical system, and that's where the vector space concept makes a relation with quantum theory. Okay. And those what I'm saying here is, what I'm highlighting is, there's a difference that those are not the real they are not the vector spaces of the kind of the kind of Euclidean vector spaces. Rather, they are of the kind of function spaces. Now what I'm basically telling you that functions can be also thought of as vectors, because you remember from our basic quantum mechanics, we know that a wave function is a solution to Schrodinger equation, which is a wave equation. So what we get as a solution to the Schrodinger wave equation is a function. Wave function is a function. It is not a vector belonging to some real Euclidean space. Okay. So this is to be noted. The vectors in vector algebra, they were not functions. They were elements of a vector space. Okay. They were not functions though. They did not depend on any other external coordinate. So here in quantum mechanics, the function, the vectors which we have, so they are the functions. So it takes us to this point of view that functions which in generally we do not think of functions as vectors, but in quantum mechanics we take functions also as vectors. This is to be noted. A very important point of view. And you may think, okay, can you give me an example where I would have seen functions as vectors? I will tell you, I have already given you example. I have given you example where you have seen functions as vectors, and those functions were solutions of this differential equation, this harmonic oscillator differential equation. And we have looked at it as solutions. These two guys are also functions. Both of them are functions, and I will write them for you. You remember them very well. So a sine of omega t, let's say, and let me call this b cos omega t. Both of them are functions. They do not look like vectors of vector algebra, but they are vectors as good as the vectors in vector algebra. Mathematically, there is no difference between these two guys. Okay, so therefore this you have to understand. This is one of the things, this is where the discomfort comes in. We become slightly uncomfortable. How is it happening? Because our understanding or the physical intuition has become used to vector algebra. I think we think that whatever is happening in the vector algebra, that is the whole story of vectors. So in other words, also I'm trying to tell you that you would not whatever vector, what you know about vector algebra is a very small part of what vectors are. Vectors are, they are much more powerful objects. That's why we use them in physics everywhere. Like, because we use them in quantum mechanics, we use them in electrodynamics, we use them in mechanics. There must be a strong mathematical reason why is it that vectors are appearing everywhere. And there are, I'm just giving you some of those examples. Why is it that they are we use vectors everywhere? And vectors are very, very powerful. What we have explored is, in some sense, the geometrical aspect of the vectors and the vector spaces, not the algebraic aspect of these objects. And in quantum mechanics, it's essentially the algebraic aspect to at the first go. It is the algebraic aspect of the vectors, where the physics makes connection to the algebraic cost in the beginning. But that's not to say that geometry does not play a role in quantum mechanics. But that definitely plays a role. We'll surely come back to those things later on. However, today and in first two lectures, we wanted to highlight that how the algebraic aspects of the vectors, like as vectors belonging vectors. I'm not telling vectors is, as you would have learned about vectors having some magnitude and direction and all that. That's coming from geometry. I'm telling you that vectors, how do you define a vector now? So vectors are elements of a vector space. And what is a vector space? The vector space has these many. It has, for us, vector space is a place. It's a very physical definition. Vector space is a place or a space where the linear superposition has happened. Okay, so that is the basic definition. There's a physicist's point of view on looking at on a vector space, so that we do not just make it in axiomatics. We are not going to do a drills in axiomatics. Okay, this is not the place for doing gymnastics of the axiomatics over here. Rather, our focus is, as physicists or as physics students, our focus is to understand physically why is it that what are these guys, what are these vectors, what are these vector spaces, and why do I use them? So I think I will take a little pause over here. I just wanted to highlight that we had already studied some examples of vector spaces. I just wanted to make some more comments about them. If there are some quick questions, Junaid, maybe you can highlight to them. You can share them if there's any question which I think is immediately relevant.
Yes, there was one question. What's the difference between a Hilbert space and a functional space?
Is that we want to continue with this physical intuition again, and try to use this physical intuition again and understand more things about vector spaces. Okay, so so this was whatever I said. I just wanted to say what is the definition of a vector space.
Sorry, Ruksame, did you listen to my question? I think my internet was.
Yeah, I think you were muted. I think you were muted. Maybe Junaid.
Okay, there's a question in the chat. What is the difference between a functional space and a Hilbert space?
Okay, so it's, yeah, okay. Any other question, any related question you think is there?
I think this is the only question. And then there is one more remark. Sir, I want to know the significance of vector spaces in real.
Okay, okay, fine. I think I get both the questions. So I think we're just it's like we're just going slightly faster than the speed of our lectures. So we will definitely, I mean, let me phrase it this way. The final thing which we use in quantum mechanics is not what we are talking about here, but definitely we are using this structure. So how we do, let me make it more concrete. How do we do in mathematics? How do we go from one structure to the another structure? First of all, I wanted to give you another piece of definition, which is a space by itself is a set. It is basically a set, plus it has some let me call it mathematical structure. Okay, and I will tell you what does that mean. First of all, I want to tell you that. Okay, so let me give an example. So let me take an example of Euclidean space. How does it follow this definition? So the Euclidean space is first of all a set. There are a set of guys over there. It's a set. But as you know, a set does not have any algebraic property. There are only two things, couple of things you do in a set. You can take unions and you can take intersections, but they are like more about set theoretic operations rather than algebraic or any other operation. So we do not do algebra with just set alone. How do we do algebra? How do we do algebra? Can we do algebra on just set alone? No, we cannot do. If you have to do algebra on a set, you have to define those algebraic operations. Like as in vector algebra, what we do, or a Euclidean space, we have a set and then we define a couple of things. We define vector addition on it. This is the mathematical structure I'm talking about. Okay. And then plus you do, as I said, some sort of a multiplication also, some kind of multiplication. Plus this is what the structure which Euclidean. Plus you also define some sort of inner product, so that you can take you have the notion of distance. You can take distances between vectors. Okay. So we have an inner product also defined on it. So these are, so how do we do it? We do it in maths. We do not study. If we have to study them, we do not study them all of them together, because it gets so difficult to understand them together. So we divide them. We go slow by slow. So we say, okay, if I have to study structure, I will first off study set plus one couple of operations on that, so that it gives me one thing. I think many of you, because we are in masters in quantum mechanics, we are doing masters in physics, many of us. So I think you are already familiar with something called a group in abstract algebra, or a group. And groups play a very, very important role in physics. But what is a group, by the way? But what is group by itself? Group is also set, plus it has only one thing defined over it. It's some sort of an addition. But that addition has to satisfy certain important properties, and then only it becomes a group. Okay. So this is to illustrate, this is to give you how do we study, how in mathematical physics, how do we explore these things. So we study them one by one. Like as a group is a very simple structure. It is simpler than the vector space itself, because it does not have any multiplication defined over it. So this is what, so what I do, how do I get group? I take a set, then I define some sort of a mathematical structure on it. I define an algebraic operation on the set, then I get a group. Similarly, in Euclidean space, I get a set, then I get these operations on it, and it becomes very, very rich. The only reason we do physics in Euclidean vector spaces is because they have the necessary algebraic and geometrical structure over there. If they did not have, we could not have done our physics in Euclidean vector spaces. And most of our physical theories are formulated in Euclidean vector spaces. Now coming back, so we are going slowly by slowly. So same thing, what we do in quantum mechanics, ultimately, we are going to, Hilbert space is a mathematical, it's just a name after a mathematician. But what exactly is a Hilbert space? So it's also a sort of a space. It has a mathematical structure. So let me, I think we are going ahead in time, so we don't want you to do that. But just to answer that question in a rather brief way. So Hilbert space is, once again, first of all, it's a vector space. Okay. Then it has more structure over here. Okay, some more structure, then it has more structure over here. So we are going to add two more, at least I think 3 more layers of structure on a vector space. Then we get to something called a vector Hilbert space. And I'll just mention here, actually we do not use the actual mathematician's Hilbert space in quantum mechanics. We use something called L2 spaces. In mathematics literature, we call them L2 spaces, not the full-fledged Hilbert spaces. Okay. So in quantum mechanics, we are going to use Hilbert spaces. And what are Hilbert spaces? Hilbert spaces are vector spaces with more structure than we have decided, than we have explored here in these lectures. And we are going to do that, but we are going to go slow by slow. We are not going to, because the aim of these lectures is not to scare you away from quantum mechanics. It's not to intimidate you, to make you, okay, that's why this is different. This course is different. We are not going to come in the course and say, okay, if you do not understand Hilbert spaces, if you do not know Hilbert spaces, in the very first lecture we talk about Hilbert spaces. That's not our way, because our way is to make quantum mechanics understandable to almost each one of us. We will find our ways, and that's the route. That's the that's the genuine route which we take in mathematical physics. We do it slow by slow. That's the systematic way to do it. So I will just that much I will say about Hilbert spaces. So we will come to Hilbert spaces when we define all the necessary structure on them, and that's what we will use in our quantum mechanics. But as of now, what we have, that part is also needed to have that's also to be needed in quantum. It's not that Hilbert space is something different and vector space is something different. No, Hilbert space is some sort of a vector space which has more structure that is needed in quantum mechanics. Okay, so yeah, that's what it is. And then other student had asked, what can we make them real? I really don't understand that question. What do you mean by making them real? Whatever we have been talking about, it's all real. I mean, it's this is the stuff which we use. I have given you physics examples, and I have given you we have been looking at solutions. We are talking about quantum physics, and what do we mean by is real? This question is not clear to me, but we will come back to this question later on. Okay, I'll continue because I wanted to highlight certain things. So we have now 3 things where we want to understand what's happening in quantum mechanics, to prepare ourselves mathematically from the background point of view. Let us focus on 3 things, and that's I think main core of today's lecture. We will try to compare three structures, 3 spaces together. So these 3 spaces are, let's take them this way. First we'll say solution space. Okay, so this is one space we will explore. Then we will have our another space which was the state space of quantum mechanics. Okay, so then we have state space of in quantum mechanics, and similarly we will have another thing which is the a vector space. I mean, Euclidean vector space. Okay, so just a minute. Okay, so I will write it here. We will have Euclidean vector spaces, and these Euclidean vector spaces we are familiar with them, so I wanted to carry them along. These are also okay. So the thing about linear Euclidean vector space is that they are full-fledged vector spaces. The vector, I mean, if somebody thinks that vector spaces we use them in quantum mechanics alone, that's completely wrong. We use vector spaces in Newtonian mechanics. We use them everywhere where we use vectors, because vectors always belong to vector spaces. That's something to be understood. There is nothing, what is new in quantum mechanics, we'll come to that, but as from the point of view of vector spaces, there is nothing new in quantum mechanics. Okay, that's absolutely nothing new. The only new thing over there is the only difference, there's a slight mathematical difference, that in Euclidean vector spaces, we have a real vector space, we have a real space over there, geometrical space, which we experience also, which we are familiar with. While as in quantum mechanics, we have a solution space rather than a real geometrical space. Okay, so in solution space, which we are have been explored last lecture also, which is the solution is of a linear differential equation, y1 and y2, and then we have the superposition is which is y, and then we have a combination. If I just write a combination, we may have ci and then yi, where I going from 1 to n, where n being the dimension of the vector space. Okay, so now what we would like to understand, what we have understood from solution space, what we have understood from Euclidean vector space, we would like to understand that, do something similar from state space as well. That's what is going to be our focus, that how do we take these things from solution space, Euclidean vector space, to quantum mechanics and understand what is going on in quantum mechanics. So that's what I'm going to fill in this box also here, this particular one, but let's take it from here. So first thing, we already understand in quantum mechanics, all the vectors which are there, first of all, before we talk about Hilbert space and the other advanced stuff, so all of them belong to, so state of a quantum mechanical system, it belongs to, it is a vector, it is a state, so-called state vector. Okay, so therefore it belongs to a vector space. That's the first thing to be noted, belongs to vector space. So this is first thing we learn about quantum mechanical system, that it is state vector, it is state space, belongs to a vector space, which means it's a vector. So this is one very, very interesting thing, that maybe in when we were studying simple harmonic oscillators and waves, nobody told us that it is solution space, it is solution belongs to a vector space. that that has not been highlighted, but here we want to highlight it. That becomes an important difference. So what is the difference? That in simple harmonic oscillator also, the solution space of a harmonic oscillator, or rather I would say solutions of a harmonic oscillator, they are also state vectors. We call them states of the system. They are state vectors, and they also belong to a vector space. So they also belong to the vector space. So there seems to be no difference. I'm fine. So like as in a quantum mechanical system, the solution of the Schrodinger equation, it belongs to a vector space. Same to same, everything is same. Same is true about a simple harmonic oscillator also, that it is solutions which are the which basically determine its solution space, which are themselves solution vectors. They also belong to a vector space. So these are the similarities. So why we emphasize on the similarities? So that we know that these things we have already learned. The same thing is happening in quantum mechanics. Then later on, as we go along, we will also highlight on the differences. But these are the similarities. Okay. And then we may ask the question, okay, you are telling me, but before I go to that point, the thing which I wanted to highlight is we have not been told that the state space of a simple harmonic oscillator is a solution space, is a function space, and it is a vector space. This is to be noted. So vector space, I am just in these introductory lectures, it is just to tell you that there is nothing new about vector spaces used in physics, because you get, as you open the textbooks on quantum mechanics, you get this impression as if there is something special in quantum mechanics and the vector spaces. I am telling you, no, I am just giving you examples. No, there is nothing special. There is no special relationship between quantum mechanics and the vector spaces. They have vector spaces arise already in vector algebra. They already arise in classical mechanics, Newtonian mechanics I'm talking about, not the Lagrangian and the Hamiltonian one. Newtonian mechanics, we use them already. We use vector spaces in Newtonian mechanics. In fact, if you remember the way we use it to tell about kinematics or the dynamics, we use it to write down that in classical mechanics, in Newtonian dynamics, what we do is that this is R of t, and in kinematics we would like to understand, we would like to this functional dependence, and this is a state vector of a kinematical system. The position vector position gives us the state of a system, of a kinematical system. So this R of t, which you use it to write down over there, then you find out the exact functional form of R of t. This R of t itself is a state vector. It is a state. It's a state vector. And which kind of differential equation it satisfies? It satisfies this kind of the vector differential equation, R of t dt2. Then it's equal to some kind of a then it's a mass over here. Then it's some force which has some form, again definitely a form. So it satisfies this differential equation. So the position vector which we use to study, that itself is a solution of a differential equation, and as a second order ordinary differential equation, it also has the properties of a solution space. So that vector itself can be thought of as a solution vector or the solution space. The only difference is that it belongs to a geometrical, something which we know in our daily life. Even the people who do not study physics, they also know there is a space out there and they can experience that space. So that is the difference. That's I mean, there are some slight differences in terms of maybe on physics side, but from the math side, all three examples I want to highlight, they are all vector spaces. I mean, mathematically, there is no difference between a state vector in quantum mechanics belonging to it's a vector. In Euclidean vector space, it's also a vector, same kind of a vector mathematically, because it satisfies the same properties, vector addition and scalar multiplication. And then you go to the solutions of a simple harmonic oscillator, or for that matter, classical wave equation, what we call as electromagnetic wave equation, or whatever wave equation you have. The solutions of that space also are vectors, and they also constitute a so-called vector space. Okay, so therefore we should broaden our horizons in understanding what vector spaces are, and we should not get shocked. There is nothing shocking, I would say. These are the things we have already studied. But then the main question which comes over there, I mean, we will come to those things. Why is it that vector spaces get related to quantum mechanics, that we will come. What are those new things which are not present in harmonic oscillator, which are not present in classical mechanics? What are those things which are present in quantum mechanical system? So those are the things which I want to highlight. And now let us, the solution space we have already studied. Now I wanted to say something here about this Euclidean vector space. Okay, so what I wanted to say is the reason we use it to do vector algebra. Okay, the reason we use it to do vector algebra without realizing is because by vector algebra I mean vector addition and all the multiplications we use it to do. However, I do not mean, I mean scalar in vector algebra we use it to study at least 3 types of multiplication. One is so-called scalar multiplication, which is important for us. But then there was 2 more types of multiplications, which is called a scalar product, and then we have a cross product defined on them. A vector space by definition does not have a cross product. A vector space by definition, the basic vector spaces which we have, you do not have a concept of the distance in a vector space. Okay, let me give you an example of that. So if I ask you, I have 2 solutions y1 and y2 as maybe as 2 oscillations. Can you tell me how far is one oscillation from the another? If I ask you this question, you will immediately tell me you are asking a stupid question. What do you mean by the distance between 2 oscillations? Okay, how do I calculate that, and is it defined? So you will definitely, if I ask you how far is this position vector from another position, you will immediately start calculating that. You will tell me, okay, you will calculate it this way. But if I ask you the same question about 2 different another vectors, like, which belong to the vector space, which is oscillations of a simple harmonic oscillator, they are also vectors, they belong to vector space. But if I ask you a question, what is the distance between 2 oscillations, and what is the distance between 2 waves? And same matter, what is the distance between 2 wave functions? Let's say if I have a quantum mechanical system, I have 2 eigenfunctions for the system. I will tell you, give me the difference between those 2 things. So to begin with, we do not have those things defined on any vector space. There is no scalar product, there is no cross product, there are no such products defined on them. So we do not have that structure. We cannot talk about distances in linear spaces. If we want to talk about distances, which we have to talk about, we will have to bring in some extra things. We will have to define inner product on it does not come packaged in the vector space. The vector space package does not have the distance, does not have inner product or any other structure. It just comes with the basic 2 things: vector addition as well as the scalar multiplication. Okay, that's why distances are not there. Now you may be thinking, why is it that Euclidean vector space we always talk about the distance of a vector, and similarly the magnitude of a vector? So the magnitude of a vector, we will explore this area a lot more, because inner products are lot more important than you would have anticipated. How do we take it? Because the Euclidean vector spaces, as I said earlier, they are not just vector spaces alone. They have more structure on them, like as they have geometry defined on them, and geometry you cannot define on just vector spaces. So vector spaces are not geometrical. I think maybe I should write it down, that you cannot do geometry. You cannot, geometry cannot be done or explored, cannot be done or explored in a vector or linear spaces. But when I say vector, I always mean linear in these lectures at least. So that's what I mean. So there is no metric, there is no distance, there is no area, there is no volume in a vector space. In a linear space, you cannot talk about these things because they are not defined in these spaces. Okay, and if we have to do them, which we would really like to explore geometrical aspect of vector spaces, then we have to bring in more things into them. Then we say, okay, then it does not remain just vector space, it becomes some bigger thing. Okay, then we move to the bigger thing. Similarly, we keep on moving to the bigger things. Okay, that's what we do in algebra. We start with some simple thing, simple structure, and then we move to the higher structures. And Hilbert space, which we have to finally explore in quantum mechanics with relation to quantum mechanics, that is at a very higher level in this hierarchy. In this hierarchy which we're exploring, it's at much higher level. But what I wanted to just really highlight here is the vector algebra. The reason we use it to do vector algebra is similarly, I mean, very similar to what I said earlier last lecture. The reason there is superposition of waves, the only mathematical reason is that because there's an underlying vector space, because the solution is, the harmonic oscillations are vectors. they are vectors. That is why there is superposition. That's why there are interference phenomena. Otherwise, we cannot get interference phenomena. You just think about it. This is the part of the tutorials which we do. In tutorials, we will explore them further. We will challenge our understanding. We'll challenge these claims which we are making in the lecture. We'll see whether this is true or this is not true. Okay, that's how we do physics. Nobody is going to accept anything which anyone says. There are no authorities over here. So whatever has been said, you have to check it, cross check it, and make sure you have to either mathematically prove it or find some physics way so that we can prove these things. Okay, so like as I just want to take you little briefly to the vector algebra, and I'm telling you the what happens in vector algebra. So whatever we have been doing in vector algebra is because there is an underlying linear or vector spaces. That is why, just because of that. Otherwise, it is not possible. So let me illustrate that. Okay, so briefly, I will just write down in this box here what is happening in a linear space. We have vector addition. Okay, we have vector addition, and in vector addition, what we have as a one property number one, is that the vector addition has to be commutative. Okay, also it has to be associative. Third thing, it has to have an identity, additive identity. Fourth thing, it has to have additive inverse. So this is what you need for a vector space if you do addition on it. Addition should have, and definitely I'm also assuming that there's a closure property already satisfied. Under the scalar multiplication, similarly, you have some more properties under the scalar multiplication, and this is the full package of a vector space. So under the scalar multiplication, what do we get? So we have another operation defined, which is a scalar multiplication. So here, what do we get is the distributivity, which means it's something like this, that if we have y1 and y2 two vectors and c1 and numbers, c1, c2 numbers, then I should have some property like that. If I have two numbers which are getting multiplied to a same vector, it should mean for me c1 multiplying y and c2 also multiplying y. Similarly, if I have c multiplying two vectors y1 plus y2, it should mean c getting multiplied to y1 plus c getting multiplied to y2. And then we should also have important is a multiplicative identity. Here also we need an identity. So these are some of the properties which we will need, and as we will explore in tutorials, these properties are already satisfied in a linear superposition. Whenever we take linear superposition, these things are already there. Okay, now let us go back. This is our definition over here. We will show that, we will see, we'll convince ourselves the reason we were doing vector algebra was because there was an underlying vector space. Let's go. So first of all, what do we have in vector algebra? We have vector addition. Okay, this is what you used to study in your school, high school or higher secondary. So you have vector, in vector addition, what do we say? We say that if we have a A vector, then we have a B vector. What I get C, but that's also a vector. This used to say that it also has to be vector, which means they are satisfying closure. We used to say that these vectors, the set of vectors which we have, they are closed under vector addition. You cannot get a scalar. You cannot get a scalar by vector addition. You will always get a vector. You cannot get out of the space of the vectors by doing vector addition. So there, then just an interesting remark here. There are other operations which you have to do if you want to get out of the vector spaces. If you want to get out of the space, there is a way. What you can do, there is an operation which some of you may be understanding now when I'm saying there's an operation which we will come to. By doing that operation, you will go from vector spaces to the underlying scalars. There are scalars also, fine. So you will go from vectors to scalars. That is the operation which we will define, but not by vector addition. But vector addition, what was the property of the vector addition? That if you have two vectors, A plus B, they always satisfied B plus A. So commutativity was there. So which you can see, it's coming from here. Then surely we had, I am just reminding you very early days of your education. So you used to study something like this. A plus, in fact, we used to kind of prove these things geometrically, that they have these properties, triangle law or parallelogram and all that things we used to study. Then we already know that it has an identity. The identity vector over here is zero vector, null vector, which we call as, which gives us basically the same thing. It gives us A. Okay, so, and then we had the concept of the inverse. Okay, which is very, very important. we have a concept of inverse, which basically means you have this guy, and then you have some I'll call a star, such that what you get is the null vector. You get the identity. I will not call null vector. You should get identity here, and identity for us is the null vector. Okay, so we used to do all these things. We used to study null vectors, inverses. Inverse of a vector is a vector which has the same magnitude, but it has an opposite direction. So you will see in the vector algebra you have all those axiomals of a vector space over there. You see, let's compare. Vector addition is closed. Yes, vector addition is closed. That's what triangle law says. That you have a vector, you multiply another vector, you will get a resultant vector, which will be different vector, but it will be a vector. It will not become a tensor. It will not become a matrix. It will not become a number. It will be always. That is what in maths we call as closure property. Then similarly in commutativity, you see vectors are commutative, they are associative, they have their addition has all these properties, and these also things which we can geometrically we use it to prove them. Say the two important elements in vector algebra without which we cannot do vector algebra. I just want to highlight, because some of the people, they think, okay, null vector, it's like null vector, okay, it's fine, we can ignore null vector, we can do vector algebra. I'm telling you, no, this is a very, very special element of vector algebra without which you cannot do anything. Same thing is the inverse. Okay, without inverse we do not have the full-fledged. You cannot just have two properties of vector addition and then you say this is a vector algebra. In vector algebra you must have these elements. Why? Because vector algebra, as I said, it is a basically the vector algebra is the vectors, these vectors, all of them, they belong to vector space. That's why they are satisfying these properties. Okay, then scalar multiplication. You had that scalar multiplication. Maybe we do not put too much of attention on the scalar multiplication. So now the one thing I want to highlight here, why is scalar multiplication important? So it is important. How do I get a inverse of a vector? Okay, let's say I have a vector A. How do I get an inverse of this guy? Very simple method. Just multiply it by -1 and you get the inverse of it. Fine. So you can, this is just an example where you think where scalar multiplication is important. I don't know otherwise how do we get it? How do we arrive from vector to its inverse without using the scalar multiplication? Okay, so this is just an example. Maybe there are some other methods which I'm not knowing, but this is one of the brilliant examples of why do we need scalar multiplication over here. So this was another property. Same thing in here also we use it to say that if you, okay, now I will remember you where this scalar multiplication you use it to study. I will remember you some of the questions we use it to kind of explore, which was if you have a vector A and you multiply it by with some scalar C, what will happen is that it will remain same vector, direction will not change, but the magnitude will become bigger in the magnitude. This is something you would have definitely studied. Okay, you would have, I mean, I'm just reminding you those things. So that thing which we used to do geometrically, that if you have a vector, you multiply it with some number, it remains the same vector, same direction, nothing happens to the direction, but the magnitude of that vector becomes bigger. That my dear friends, was a scalar multiplication. That is the power of scalar multiplication, and that you need if you need to do certain things. Fine, you always need to multiply them with, and then only you get a bigger numbers, bigger. You can change. So what you do in vector algebra, how do you change your magnitude of a vector without changing its direction, is by scalar multiplication. And definitely this is, I don't have to prove it for you that if I multiply it with one number, just one unit value, if I multiply it with any vector, it will remain the same. I will have the same guy over here, and that's what its multiplicative identity. Okay, so I'll just say these things. I mean, I don't want to spend too much of time on it, but I just wanted to bring it to your attention that whatever vector algebra we have studied in very early classes, that vector algebra, first of all, is the vector algebra over there, is all those properties are because the vectors belong to a vector space, and the definition of a vector space are these things whatever you have done already. So this is just to make you very, very comfortable that whatever vector spaces we are going to study in quantum mechanics, so that we already have background, we are just highlighting them, especially the mathematical aspects of them, we are just highlighting them, and with that intuition going forward, now, I mean, when we go from third lecture onwards, we will deep dive into quantum mechanics. It is mathematical formalism. We will be writing everything. As of now, I am writing things in a very familiar language, but we will shift to, very soon we will shift to quantum mechanical formalism, and then you will start making correspondences, and I will be. So these two lectures were very, very important, because they were for everybody, because whether he goes to quantum mechanics or not, it needs to be understood. How do we understand what do we mean when we say we want to understand the mathematical aspects of it? This is how, I mean, if somebody gives you you may be understanding triangle law of vector addition, but you may not be realizing that it belongs to a vector space. But that's not doing maths. You are just doing some algebra, one small addition property of it. You have, in maths, we have to realize mathematics is about studying underlying mathematical structures. That's what it is about. A lot of mathematics is just about that. Like, as in mathematics, we study symmetries. And how do we study symmetries? We study symmetries by studying groups. And people have explored their full life careers in understanding the groups, various properties of the groups. And even now they have been explored. They were introduced very early on. I think more than a century ago, group structure was introduced in mathematics. But people are studying them even now, because mathematical understanding means understanding the underlying mathematical structures. It is not sufficient that you know some of the rules of the game and then you think you are doing. That is why when we go to quantum mechanics, we have to understand these underlying structures. What is a vector space? What is the inner product defined on that? Why do I need it? And what is the completeness? What is the completeness of a vector space? What is the compactness of a vector space? And all those things. Then only we get on to then. So, in some sense, the state vector of a quantum mechanical system as a mathematical object, it is much richer. It is much powerful and more complex than the state vector of a simple harmonic oscillator. And there is difference. But having said that, we will be coming to the harmonic oscillator again and again and again. Just one example: particle in a box. When you write down your Schrodinger equation, you apply the boundary conditions. If you remember those things, you will finally, at the end of the day, the equation which you have to solve is actually a harmonic oscillator equation. This I pose you as in the lectures. I will be sending you teasers just to ignite some curiosity in you. Why is it that your Schrodinger equation becomes simple harmonic oscillator equation when you apply the boundary conditions in a harmonic oscillator? Same happens in many other cases. We will explore them. So this is just a teaser for you. Just think about it. What is the connection? And is it related to what I have said in the lecture, that the vector spaces of harmonic oscillators and the vector spaces of Schrodinger equation as a solution space, they are strikingly similar in physics way also, and mathematically they are very similar. Okay, in fact, at a linear space level, they are basically same. So going forward, when we go to the next lecture onwards, we will be understanding the complexities of this of the state space of quantum mechanical system. But whatever we have explored till now, this is going to offer us the basic background, basic mathematical background, where from we can take forward. So for today, I will stop here, and I would really like to take your questions. And before I go there to the questions of today's, we'll see how much time we have. But there are a couple of questions which were raised in the last lecture. I just want to get back to them. One of the questions which was from Shahid, he asked, why is it that in quantum mechanics books they ask? I think he would have got the answer by now, but let me still say it. Why is it that these quantum mechanical books start with they talk about these spaces, inner product space are defined over there. So definitely, Shahid and everybody of you. So in quantum mechanics, it is not sufficient to have just linear spaces. If we have to understand the full physics of quantum mechanics and full mathematical structure of quantum mechanics, linear space is not sufficient. Linear space is the just basic thing. This is the beginning of the story. Okay, then we will be without, like, as if you do not have inner products defined in quantum mechanics, you will not be able to take expectation values. You cannot take expectation values. You cannot also calculate the norm of a vector, because norm of your wave function, you cannot do the normalization. Without inner products, neither can you do normalization, nor can you take expectation values. But we need both of them. We need both the things. They are very important ingredients of quantum mechanics. So therefore, we need inner product. But inner product is not part of the linear space. We have to buy this stuff. It is like linear space is a package. In this package, we do not get it. What do we do? In our daily life, what do? We go to market again, we buy that stuff. So inner product, if we want to have inner product in our vector space, we have to buy it, and then we have to make a bigger package. Similarly, if we want to have something more also, which we will talk about that's called the completeness. That's the spectral decomposition. You can always write down any wave function as an expansion of its eigenfunctions. So that's a very, very special property, and you just do not get it very easily. And one more difference which I want to highlight here, all the vector spaces which I am talking about, they are finite dimensional vector spaces. All of them, like as I talked about solution space of a harmonic oscillator, it is just two-dimensional. Very simple thing to deal with. Similarly, the vector algebra which we dealt with, that was a dimension, had a 3 dimensions. It's a 3-dimensional vector space. The real Euclidean vector space is 3-dimensional. Solution space of harmonic oscillator is 2-dimensional. But when you go to the quantum mechanical system, you would have heard, but we will explore. If I ask you why is it that, I don't know whether you will be comfortably telling me how is that the vector space of a quantum mechanical system is infinite dimensional. We will see how is it infinite dimensional. Okay, and because you have to deal with an infinite dimensional, and it is not the usual vector space, it is so-called a function space. You have to deal with infinite dimensional function spaces. It brings in lots of mathematical challenges for us. Okay, that is why we have to bring in many new things, like as when you try to deal with momentum operator and it is eigenspectrum, it's very, very difficult to deal with. That's why you would have heard of something called a box normalization. You always put your particles in a box. There's a very special reason why is it that we put our particles in a box. That has something to do with the fact that the system you are dealing with is an infinite dimensional solution space. That's why we apply those periodicity boundary conditions. Okay, so but we will come, this is the exciting stuff which is going to come in future. We are going to do a lot more exciting stuff. I mean, amazing stuff, the amazing subject which quantum mechanics is. We're going to explore that, all of that, but that will come later on. But today I will stop, and I think this was the answer to the this question. And there was one more question before I go to the new questions. I don't remember who has asked that, but the question was that about what is the physical reason? How do I understand that this null vector which I was talking about? Okay, in a linear superposition, I said it's a linear superposition gives us vector spaces. And so how do we get these null vectors over there in a linear superposition? So I think there has been, this question is very important. I will but I don't want to spend too much of time on it. I just want to make a brief comment. Let me make the brief comment here. Many people think that, as I was saying earlier, this null vector is not, they think it's not physically important because it is 0. They think, okay, because it is 0, that's why it is not physically important. Let me tell you why is this guy important. First of all, let's say we have two waves, y1 and y2 are two wave functions and waves, and they are doing not the constructive interference, they are doing destructive interference. What do you get out of that is my question to you. What do you get when you have same wave, same magnitude, same phase, opposite phase, anti-parallel phase, and they are interfering with each other? Magnitude is same, amplitude is same, and then they do the destructive interference. What do you get on the screen? How do you represent that mathematically? That's my question. I will just give it in that way. I will answer it. So the answer to that question is that guy over there is a null vector. Now the point over here, when you draw a coordinate system, so what is here, this, how do you represent this guy over here, which we call the origin? The origin of the coordinate system, mathematically, how do we represent it? Who is this guy? I mean, if you have to write a vector for it, what kind of vector? What will be its coordinates? What will be its x component, y component, z component? You will notice that it will be 0, 0, 0 in all the 3 directions. So that's another reason, that's another place where we need null vector, the physical reason. Third reason, let us say in dynamics, we have two vectors. We have let's say on the one side we have the net force F. This is the F net on one side, and let's say now we have a tug of war is happening. We have a tug of war going on, and we have one group on this side and another group on this side, and the net force F net is here and F net is here. There's a one point when we have they are balancing each other. That balance is a very, very important point. It is called the dynamical equilibrium. The dynamical equilibrium, how do you represent that dynamical equilibrium? If you do not have a zero vector available to you, how do you say that the net force on one side and the net force on other side is canceling each other, and then we are getting the dynamic equilibrium? So these are just 3 examples to highlight how important zero vector is. So without zero vector, there is no vector algebra. You cannot have vector spaces. That is the short and brief answer to that question. So let's move forward. So let me stop sharing for a moment. Okay, so I think we will. I just saw a few of the questions. I'll just take one of them. Shahid has another question, but I will come to them. Bashir has, I think, asked something about dual vector spaces. So we will come to them. Dual vector spaces are very important. But all those, I think, you are not asking questions about what the content of the lecture today. So it seems as if you are all compatible with whatever I have discussed. It looks like you are all compatible, which is a good sign. But I'm slightly doubtful whether you are all compatible with everything what we have discussed. That's why we have started from here. There'll be many amazing things which will be coming up but they will be the questions will be discussed in upcoming lectures, like as the concept of the dual vector space. In quantum mechanics, you cannot do stuff. In quantum mechanics, it's not sufficient to have just vector space alone. You have to have a dual vector space also with you. Okay, so I think I will stop because we have a time limitation. So I'll stop here, and then whatever questions we have to take, we will keep on. Definitely these questions will be collected. I have all your questions available to me after the lecture, so I'll come back to them in the next lecture, or I will if you want to have an individual discussion, I think I will take that also. But for today, the last thing, Junaid, Junaid, maybe we can stop the recording. I just have to basically say certain informal things.